Hello, we're glad you've joined us for this live webinar, Spectroscopy Techniques for Tomorrow's Scientists, Evolving Technology for the Teaching Laboratory. I'm Judy O'Rourke of LabRoots, and I'll be moderating this session. Today's educational web seminar is presented by LabRoots, the leading scientific social networking website and provider of virtual events and webinars advancing scientific collaboration and learning. It's brought to you by Thermo Fisher Scientific. Thermo Fisher is a world leader in serving science, whose mission is to enable customers to make the world healthier, cleaner, and safer. For more information on our sponsor, please visit www.thermofisher.com. Let's get started. You can post questions to the speaker during the presentation while they're fresh in your mind. To do so, simply type them into the drop-down box located on the far left of your screen labeled Ask a Question and click on the Send button. Questions will be answered after the presentation. To enlarge the slide window, click on the arrows at the top right-hand corner of the presentation window. If you experience technical problems seeing or hearing the presentation, just click on the Support tab found at the top right of the presentation window, or report your problem by typing it into the Answer a Question box located on the far left of your screen. This is an educational webinar and thus offers free continuing education credits. Please click on the Continuing Education Credits tab located at the top right of the presentation window and follow the process of obtaining your credits. I now present today's speaker, John Frost, Ph.D., the Product Manager for Thermo Scientific picoSpin NMR spectrometers at Thermo Fisher Scientific in Madison, Wisconsin. He holds a Ph.D. from the University of Wisconsin in analytical and physical chemistry, where his work contributed to multiple patents, and a master's degree in organic chemistry from Michigan Technological University. With a deep commitment to the education of the next generation of scientists, Dr. Frost has co-authored several papers in the Journal of Chemical Education, served as adjunct faculty, and actively participates in multiple outreach programs for high schools. Dr. Frost will now begin his presentation.
Thank you for that kind introduction. So today's webinar is Spectroscopy Techniques for Tomorrow's Scientists, Evolving Technology for the Teaching Laboratory. And we're going to briefly review some of the most common spectroscopic techniques in the chemical sciences curriculum, how they fit in the curriculum, some examples of laboratories and ways to communicate the technique to your students, and a few examples of how they're used in the real world. So getting right into it, we are all familiar with the electromagnetic spectrum and the fact that students are typically exposed to three types of spectroscopy in their high school and undergraduate chemical careers: ultraviolet and visible spectroscopy, infrared spectroscopy, and NMR. Conveniently, they're kind of arranged from right to left in this particular graphic as well. And that's the way that students typically encounter them. They'll, in the high school and maybe freshman general chemistry laboratories, they'll experience visible and potentially UV visible spectroscopy. When they get into that sophomore level organic course, they'll start to run into FTIR and maybe be exposed to the basic theory and interpretation of NMR spectroscopy, and then again in their senior years, either through P-Chem or a senior level instrumentation class or in graduate school, be exposed again to these techniques at more of a hands-on and at a more advanced level. So to kind of summarize again the different techniques and how they're used, we've got UV visible, and we'll split that into the ultraviolet portion and the visible portion. Ultraviolet being from 50 to 400 nanometers, although we typically work between 190 and 400 nanometers. But in either case, we're working with fairly high energy radiation, which excite valence electrons, and is typically used to determine concentration. There is some qualitative measurements that can be taken with these techniques, but typically we're simply measuring concentration, and we introduce visible and UV visible in either the high school or first year undergrad courses. Infrared, as I said, comes in that second year undergrad. This is a lower energy radiation source in the infrared. and instead of exciting valence electron, we're vibrating covalent bonds. So we're just looking at perturbing those just enough to increase those oscillations. And from that, we're getting functional group information, information about bond type, and from that, we're starting to get a lot more qualitative information about the molecule itself. And then we get to NMR with radio frequencies, extremely low energies, and we're perturbing the nuclear spin states to learn more about the magnetic environment of the nucleus, and thereby get information on a lot of qualitative information on the molecule itself. So the structure, but also concentration, solvent, temperature, and a number of other things. I'm a little biased because I am the NMR product manager, but I think there's a lot of information there. And we typically introduce this technique to students in that second year undergrad organic course, but don't, in many cases, allow them access to hands-on use the instrument until that senior level instrumentation course or even graduate school. So jumping in a little bit more in depth to UV visible spectroscopy, we're looking at the portion of the spectrum between X-rays and infrared. And while the instruments themselves are typically fairly simple to operate, it has great analytical results that are very accurate, very reproducible, even at very low concentrations. So it's a very useful technique, and we see it used in a lot of different industries. When we introduce the concept from an instrumentation side of things, we show them the white light source goes through an entrance slip to a monochromator. That splits that white light into all of its individual colors, and we use an exit slit to select a single wavelength, which is then transmitted through the sample to the detector, and we get our numerical readout. From more the conceptual standpoint, we talk about the ground state, and with the absorption of a photon of light, if that photon matches the energy level difference between the ground state and the excited state, that electron will be excited, absorb that molecule, that photon, and be excited into the excited state when that's the absorption. And that's really as far as we take it before we jump into Beer's law and start talking about the practical measurement of various components using UV visible spectroscopy. And so here's a nice entry-level lab where we look at some very common food dyes, determine the peak absorbance for each of those dyes, and then build a calibration curve using blue food dye, which can then be used to determine the concentration of the dye in a commercial sports drink. So giving them a direct, relevant, relatable link to the rest of their life. When they come back to it again at that senior level, we start thinking about not just that simple transition from one electronic state to the next, ground state to excited state, but we start looking at, hey, there's fine structure within there, and you can actually look at the individual vibratory nodes within that energy level. And so we can look at the fine structure using a instrument with a little bit higher resolution, lower bandwidth, and from there we can start looking at perhaps the bond dissociation energies for various halogens. So in this example, you would put a few crystals of iodine in the bottom of a 10 centimeter gas cell, allow that to sublimate, and then you can measure the fine electronic structure there related to the individual vibratory levels within that electronic energy level, and from that calculate out the bond dissociation energy for these various halogens. From an instrumental advancement point of view, the technique is very mature, but there's still progress being made. And one of the biggest advancements in recent history has been the introduction of microvolume UV vision measurements. So instead of using a 1 centimeter cell or a half centimeter cell, instead you can remove the cuvette entirely and pipette 1 to 2 microliters of sample directly on a pedestal. Now, you can kind of see in this upper right-hand picture, there's an arm that will then come down, make contact with that droplet, and then relax out to pull that droplet into a liquid column. And that column acts as your measurement zone. And with a very precise measurement of the distance between those two contact points. You have your path length, and you just transmit through via optical fibers and take your measurement that way. So huge reduction in sample volume requirements, and that's opened a lot of new applications within the technique, eliminating a lot of the cuvettes, especially in the UV region, are quite expensive, and just speeding up and simplifying the process overall. So as an example where we might see this used in an advanced biochemistry laboratory or even in industry, we can look at sample contaminant identification. And in this case, we acquire our spectrum, and this would be on a purified DNA sample, and we want to look at that spectrum and identify, is there potential contaminants from the extractants or from proteins that may have been extracted alongside it. And we can look at some different ratios of the absorbance measurements at different wavelengths and use some chemometric modeling to analyze that data, say, hey, there's something going on here, and then using chemometrics extract that to not only determine what the contaminant is, if it's a protein contaminant or phenol, which is a common extractant, but then also to correct the total absorbance for the DNA so that we have a true DNA concentration value rather than just the combined from the DNA plus the various contaminants. And a way to bring this back to the students is, in addition to folding this into the existing software, there's little training videos and support pages built into the software to give students that onboard support to refresh their memory on, oh, that's what we're doing now. This is how this is related. In more of a conventional sense, heavy metal testing is very important, and we see that a lot in industry. So iron in water is something that needs to be measured according to EPA guidelines. And so here what we'll do is reduce all the iron in a water sample to iron 2, complex that with phenanthroline, and then that red-orange solution can be measured against a calibration curve using some external standards and to determine the iron concentration. So you don't need atomic absorption in order to do this measurement. You simply complex the iron to phenanthroline, and then you can make that measurement using visible spectroscopy. Moving on to the infrared portion of the spectrum, you can see we've shifted to some lower energy, and although the infrared portion typically spans between 14,000 and 200 reciprocal centimeters, we typically, for an education perspective, only work between 4,000 and 400 reciprocal centimeters. So we're looking at the mid-wavelength infrared group frequency and fingerprint regions. So here we already have bonds that are naturally vibrating just through the normal processes, and what we need to do is find a wavelength of light that will be in resonance with that natural energy of vibration. And so as long as they're vibrating and we find that matching resonance, we then absorb a photon of light. That photon increases the amplitude of that vibration, and we see the absorption. Now, one of the requirements for this is that the molecule must have a dipole moment. So while they cannot be ionic bonds, we do need to have a more of a polar covalent, or at least somewhat polar covalent bond in order for this to work. So obviously we can do nonpolar absorptions, but a proton-proton bond is something we can't measure because there is no dipole moment, and so there's no absorption possible. So we don't see that with nitrogen-2 either. Kind of bring it back to different model. You can see again, we're looking at the energy diagram, and we're looking at individual vibratory energy levels within that. And those vibration levels can be in a number of different planes. We can have antisymmetric or symmetric stretching, scissoring, wagging, twisting, rocking, and this is a great learning opportunity for students to understand not just the theory in this two-dimensional practical sense with the math and things like that, but also to get a little movement into your classroom as well. Something that was very popular when I went through school was the infrared spectra dance, and you can have your students practice these antisymmetric stretching and symmetric stretching using their arms, and if you really want to get fancy, you can throw in a third nucleus, and now you've got a leg involved, and it gets quite humorous quite quickly, but it's a great way to get the students to engage with the material and really understand what these different transitions are and how they all relate to each other. And these aren't simply just vibrations for the sake of it. They give us a great deal of information about the structure of the molecule itself. So all of these vibrations are very well understood. It's a very mature technique. And so we can relate CH stretches to aliphatic carbons or to CO carbonyl stretches and all sorts of different functional groups and bond characteristics. And this is well known, well documented, and you'll find lots of tables online and charts. We even have a wheel that allows you to select the wavelength or reciprocal centimeter absorption, and then look at all the possible absorptions that might be associated with to relate that to that structure. From a laboratory perspective, the synthesis of aspirin is a very common one, and one that we'll keep coming back to in this presentation because of its ubiquitous presence in the sophomore organic chemistry lab. And so here we've got the salicylic acid being reacted with acetic anhydride to form aspirin. And if we look at the infrared spectra of the starting materials, you see we have a very strong OH phenol stretch. We've got that carboxylic acid absorption as well in a couple different places. And then we have the C double bond O acetic anhydride peaks as well. And then when we move to the product, the acetylsalicylic acid, you see there is no phenol hydroxyl group, and we've lost that same stretch. Same thing with the acetic anhydride. Peaks have gone away, and instead we've formed that ester, that CO ester. So it's pretty clear, and the students can look at this, relate it to their tabulated data, and justify their conclusion that the reaction was indeed successful by analyzing these individual spectra and the spectra of the final product. Similarly, wintergreen oil gives a very pleasant odor in the laboratory. Can be, you start with salicylic acid, that same starting material, but in this case react it with methanol. So we've got that very distinctive, broad, strong hydroxyl stretch out at the 3300, and with the formation again of the wintergreen, the methyl salicylate, that hydroxyl group is gone, and so we lose that big broad stretch, and we also lose the carboxylic acids as well in favor of the ester. So the analysis of the two is very similar. From an instrumental perspective, one of the biggest advancements is the introduction of attenuated total reflectance as a way to sample your measurements. In many cases, gone are the days of KBR pellets or salt plates, and instead what we're using is attenuated total reflectance. And how this works is a beam of light is injected into the crystal at a particular angle, at which point it will undergo a process called attenuated total internal reflectance. At the point of total internal reflectance, 100% of the input light is reflected out. There's no loss of the light intensity due to reflectance. And so you get 100% transmission out the other side of the crystal. However, the physics shows that at that point of total internal reflectance, you will form an evanescent wave. And that evanescent wave is shown by these small, decreasingly gray triangles that extend up. And what those are evanescent waves that extend out beyond the point of total internal reflectance, but don't detract from it in and of themselves. They do, however, have the ability to interact with a neighboring substance and couple light into that for absorption purposes. So if you have a sample in contact with that crystal, and it needs to be in contact, so with all these ATRs, you'll see a little arm that comes down and presses the sample down, because the evanescent wave only extends a fraction of a wavelength into the sample. But so these are surface level measurements. But when it is in contact with that point, then the evanescent wave will couple light into the material, and you'll allow absorption to occur without any direct interaction between the light itself and the sample, which is pretty interesting stuff. But it really simplifies getting your students through a given lab quickly and moving things along. Once we get into advanced theory, we start talking about the microluminescent interferometer, interferometry, and using fast Fourier transform in order to convert that time domain spectra into a frequency domain, or time domain interferogram into a frequency domain spectrum, and then the difference between the transmittance and the absorption spectra, and working with both of those. And in an industrial setting, we see FTIR used in many different industries. It's a very useful technique that pops up almost everywhere. But one of the big ones lately has been for the rapid detection of phthalates. And we worry about phthalates in consumer products, and especially when it comes to baby and small children's toys. We want to keep phthalates out of there. And FTIR, especially with ATR, is very useful as a fast screening tool. So you simply need to put the material in question in contact with that ATR crystal, press down on the little arm, and very quickly you'll be able to identify the presence of phthalates from the orthoaromatic group. It has a strong absorbance of around 741 to 745, and then they also have characteristic doublets at 1600 and 1580 from the aromatic ring stretching. And so if we look at a spectrum of this plastic that in this case does have phthalates in it, we see very characteristically that 745 and the doublet there at 1580 to 1600. And so very quickly, within a matter of seconds, we can say, yes, the sample does in fact contain phthalates. All right, moving on to my favorite, nuclear magnetic resonance. We're pushing all the way past ultraviolet, visible, infrared, and now we're into the radio spectrum. So this is FM broadcast range between 1 megahertz and 1 gigahertz, so about 300 meter to 30 centimeters. But we're also covering the high frequency, very high frequency, and ultra high frequency. So the VHF and UHF that some of us may remember from the old televisions where we had to select the different channels by hand. But if we look at the NMR spectrum and NMR theory, here we're not looking at high energy radiation. We're looking at very, very low energy radio frequency. And what we're doing is we're looking at the nucleus of the atom itself. And I'm going to try to split this into what we see taught typically at the high school and organic sophomore level versus what we see beyond. So you'll get a little bit of theory of both, but we won't dive too deep in either case. So what we're looking at is we're looking at the nucleus rather than valence electrons or vibrations as we are with the other ones. Instead, we're looking at the nucleus itself. And so if we consider hydrogen, which is where we do most NMR from a technique standpoint, we're looking at the proton. So proton has a charge. It also has a nuclear spin state associated with it. And if you have a spinning charge, you have a particle that will behave like a small magnet. And these magnetic moments are oriented randomly in space in kind of a ground state situation. But if we then introduce a outside field, a magnetic field, they are forced to either adopt an orientation with that external field, which is the low energy state, or against that field, which is the higher energy state. Now we have two different energy states, just as we do with UV-Vis, and that allows us to have a Boltzmann population distribution and therefore to do some spectroscopy. And talking about the two different energy states and the relationship of that to field strength and the size of the magnet is oftentimes where we stop the theoretical discussion of NMR at that entry level. When we come back to it, we start to think about, well, how do we actually record the measurement? And that's where it really gets interesting. So if we have these individual nuclei, and the majority of them are in the lower energy state, and so they are oriented with the external field and what we call the z-axis. If we kind of sum them all up, they're all pointing, on average, we get one magnetic moment that is, or magnetic field vector that's straight along the z-axis. Now these are not pointing straight up, just as a top wobbles. These wobble too with a characteristic frequency, and but if we average everything together, we get one magnetic field vector straight up along the z-axis. If we bring in a radio frequency coil and we transmit at the frequency that these individual protons are naturally processing, called the Larmor precession frequency, we then cause them to become phase coherent, so they're all tipped to the same direction at the same time, and that causes a shift in the magnetic field vector into the XY plane. At that point, we can turn off the transmitter and allow those nuclei to relax back to the z-axis in their ground, what you could consider their ground state. And so what we're doing there is we're looking at their free relaxation or decay back to that ground state, and we're doing so as they induce a charge, because remember, we're looking at these nuclei as if they were small little magnets, and whenever you have a magnet that's moving inside a coil, it's inducing a current in that coil. And so we call it the free induction decay. So it's the free decay back to the z-axis, and as a result, we're inducing that current, and that causes the FID that is unique to each proton under observation. Now, if we look at something like ethanol, we've got three chemically distinct types of hydrogen. So we've got the three hydrogens attached to the methyl group, two to the methylene, and then one in that hydroxyl. They all have their unique characteristic frequency and will result in their own FID. Those all get piled on top of each other during the measurement, however, and so we get some very interesting squiggly lines, which through the same Fourier transform process that we used in infrared, we can use to transform it from the time domain into the frequency domain, and we get an individual unique signal for each of the three hydrogen types. Kind of jumping back to what we introduced at the entry level in that organic chemistry class, we spend most of our time talking about how to interpret the spectrum. So just like we spend a lot of time teaching interpretation of the infrared spectrum and the organic chemistry level, we do the same thing. That's where we provide our focus for NMR as well. We talk about how many signals and how those relate to the individual hydrogens and multiplicity, and that's how an individual signal may split into more than one peak. So if we look over towards the right, you see a group of three peaks. That's referred to as a triplet, and that's one signal, but it is three peaks, each with a distinct energy. And then we look at the integration and how that's inherently quantitative and can give us information not just about how many hydrogens make up that signal, but also if they're mixtures and how we can use that to pull out quantitative information about the sample. From an instrumental perspective, the major advances here have been the instrument itself. For many years, NMR instruments were large floor-mounted units, the smallest of which weighed in at over 800 pounds. And in late 2011, the picoSpin 45 was introduced, weighing in at only 10.5 pounds at a full 45 megahertz fast Fourier transformed instrument meant that students at smaller four-year universities, community colleges, and even high schools would no longer have to rely on photocopied NMR that were distributed to their students at the end of the lab, or for those universities that did have a high field system available, no bored grad students having to collect everyone's samples and then run them overnight, either manually or with an auto sampler. Instead, students had the ability to bring the technique right into the lab, right on the bench top, and run the experiment themselves and see how their sample turned out, not how a generic one did. Ways that we've introduced this at various levels, because the instruments were so large and expensive in the past, it was really a closely guarded technique, but we've seen it grow in popularity and be introduced to students of all levels. And so we've seen a lot of development in how the technique is introduced to students, even at the high school level. And that multiplicity I was talking about before can be very easily used to demonstrate to students quantum mechanics. We talk about quantum mechanics for the first time in high school level chemistry classes because it's so important to everything we do in chemistry and physics. But there's really very few ways to show students that quantum mechanics is anything more than a mathematical trick that some super smart physicists played with in the 1900s. But we can show that to them, and we can relate it to them very easily. You can think of yourself and your own mood and relate that to a neighbor. And if you have one neighbor and that neighbor is happy and you're happy, that's one relationship with one combined energy. If you're happy and they're not so happy or grumpy that day, that's a different, that will affect you in a different way and lead to a different energy of your combined state. And so if you have one neighbor, you have two possible orientations. You're happy and they're happy, you're happy and they're sad. And so you get two different energies, you get two different peaks. And we see that in the upper right-hand corner. You see we have a single signal under interest, but it splits into two different peaks because of the effect of that neighboring quantum spin. And you can extend that beyond two neighbors or four neighbors or however many neighbors you like. And you can add levels of difficulty by having the students calculate the change in energy of the spin states using the J-couplings. And you can extrapolate that as far as you'd like. We've had professors extrapolate this simple demo all the way into a graduate level quantum mechanics experiment for physics graduate students using Hamiltonians and calculating all sorts of things. So it's a really versatile little tool to introduce and show students one of these basic concepts is more than just academic hyperbole. Another concept that comes up in every general chemistry course is percent composition. And so you can look at some very simple solutions of rubbing alcohol or vinegar in water. And in those cases, you can neglect multiplicity and everything about the NMR itself and just focus on letting the students warm up to the use of instrumentation, realize that there are other ways to measure things that are colorless and so may not have a visible absorption. And so we can just ignore the multiplicity of the NMR spectrum, focus on the integration, and use those relative integration ratios to calculate concentration in a number of different ways, and molar concentration, percent by weight, percent by volume, things like that. Of course, at this point, I have to bring back the synthesis of aspirin or wintergreen oil just to bring everything together. And so salicylic acids subjected to esterification to produce either one of those, you end up with two very different NMR spectra, and you have all the multiplicity and J-couplings you need to pull out each of the individual unsubstituted aromatic ring portions and look at the effect of that acid and where it shows up, and kind of relate these to the spectral interpretation that students are expected to learn at that organic chemistry level. an advanced level or an industrial setting, you see NMR used in a variety of different ways for reaction monitoring and all sorts of things. But one we see a lot in industry is determining the molecular weight of polymers. So polymers start with these simple chains and then they're reacted through a process which causes them to grow and grow. But determining the average molecular weight of that composition is something that manufacturers work with because it determines a lot of that polymer's characteristics. And so they need to figure this out. And NMR is one of the preferred techniques, and it's related directly to the percent composition lab in terms of the mathematics is very similar. Again, we're kind of ignoring the multiplicity. We're ignoring individual resonances, and we're focusing on, well, here we've got one area we know is related to this. We've got another area we know is related to that. And we can look at these ratios and combine that with the other information we know about the starting material and determine things like the molecular weight, the composition, the hydroxyl number, all of these things that determine a polymer's physical characteristics and are very important in their daily lives, but without all the fancy math that we sometimes see in interpretation of small molecules. So with that, I would thank you for your time and encourage anyone looking for more information to visit our Chemistry in the Classroom webpage, where you can view more information on the labs we have available. We have a number of different laboratories that you can incorporate into your classroom, and you can also learn more information about our Nicolay Summit FTIR spectrometer, our picoSpin 80 and picoSpin 45 Series 2 NMR spectrometers, and our Genesis line of UV visible spectrometers. At this point, if there's any questions, I'd be happy to answer them.
Thank you, Dr. Frost, for your presentation. So a quick reminder for our audience on how to submit questions. Simply type them into the drop-down box located on the far left of your presentation window labeled Ask a Question and click on the Send button. Dr. Frost will answer as many questions as time permits. The first question is, how can I get all my students through the laboratory, collecting data on their sample and processing the data?
Right. Well, that obviously depends on the number of students in your classroom and the number of instruments available. But we have designed all our instruments to be classroom friendly and to really focus on throughput. And so we have things like our Omnic Anywhere and the Thermo Fisher Cloud that allows data to be directly uploaded to a network drive or a cloud storage drive. And that allows students then to process that offline so they can go up, use the instrument, but do processing away from the instrument so that the next student can come and get their sample analyzed as well. Keep things moving quickly and easily.
Thank you. Next one is, what is the difference between your more affordable spectrophotometers and your advanced models?
That's a great question. Really, with all of our instruments, the difference between the more affordable options and the more advanced instruments really comes down to specifications and the ability to adapt to new labs and new applications. So with the more affordable instruments, you have kind of larger specification windows and not a lot of accessories that are able to adapt to them. Once you get to the upper level models, you have tighter specs, better performance, and a lot more accessories that allow you to adapt a given instrument to take a number of different measurements in a number of different ways. So maybe they're temperature controlled cell holders, fiber probes, ATRs, or just better performance, reaction monitoring accessories. All sorts of different accessories start to play in the game, and that allows you to kind of take it from a simple bench-mounted, one at a time measurement to a more automated measurement or a more focused measurement for this particular application that I can then transition later to do a different measurement somewhere else.
Thank you. The next one is, have you had many high schools use your instrumentation?
Yes, we have. We've had a number of instruments. The Spec 200 is a staple within the high school market, but Genesis is taking off as well. And then within, with the high schools that offer AP and IB classes, there's been some changes in the rules that have encouraged more use of hands-on instrumentation. So we're seeing a lot more infrared and even NMR being adopted by high schools.
Thank you. What other industries are spectrophotometers commonly used in?
Spectrometers are used all over the place. We see them in the pharmaceutical industry, polymers, batteries and energy storage, solar energy, thin films, plastics, petrochem, food testing, hospitals, life sciences. Spectroscopy is the way we use light, which is one of the most available sources of energy we have to measure the world around us. So we use it all the time, pretty much everywhere we need to make a chemical measurement. We'll, in some way, shape, or form, turn to spectroscopy. So you'll find it just about everywhere.
Thank you. It looks like we have time for one more question. What kinds of warranty and maintenance are associated with these instruments?
So all of our instruments, as I said, were kind of designed both with industrial applications in mind, but also with an eye towards our educational partners and how they might be used in the classroom. So we've taken steps to make sure that our instruments are very durable, and as a result, we've been able to offer industry-leading warranties on all of our instruments. So those industries range from 2 to 10 years, I believe, and your sales representative would certainly be able to talk to you more about that. But from a maintenance perspective, they're all very low maintenance. I would probably argue FTIR is maybe the most maintenance intensive, and in that case, you really only need to change desiccants every few years at the most. So so maybe desiccants were 1 point during the life of the instrument, but beyond that, all of our instruments designed for the classroom are intended to just be plugged in and used and be really robust. I remember a few years ago, a few of our sales reps were really advocating for us to drive over some of our spectrometers with a truck because they believed that they would still work on the other side of them. So they're very, very durable, require very little maintenance, and are backed, as a result, are backed by some very strong warranties.
Well, I would like to once again thank Dr. Frost for his presentation. Do you have any final comments?
Just thanks again, everyone, for taking the time today. If you have any additional questions, feel free to reach out to me or through the email link provided to have your questions answered directly by myself or the appropriate technique expert.
Well, thank you again. And I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today will be addressed by the speaker via the contact information you provided at the time of registration. We would like to thank our sponsor, Thermo Fisher Scientific, for underwriting today's educational webcast. This webcast can be viewed on demand through October 2019. Lab Roots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.